Hey, what's up, guys? Chung here again. So, so today I want to talk about this LeetCode problem here, 1425, constrained subsequence sum. Yeah, this is like a hard problem, and this one, this problem like actually consists of few sub-problems. So let's take a look at this description first. So you're given like an integer arrays, right? And the integer k. Notice that the integers in this array could be positive and also negative. And you need to find the maximum subsequence so that its its sum is the max. And what's the constraint for the subsequence, right? So the constraint of the subsequence is that uh, any two any two of the consecutive numbers in the subsequence, its distance, the index, right? The index between those two cannot be greater than k, right? So what does it mean? It means that, for example, this one, if the k equals to 2, right? And for subsequence, you can basically remove any letters, any element from the existing array, and while keep the remaining elements in their original order. For example, here, right? So from if the k equals to 2, it means that you can skip one element at most, right? For example, here 10, 2, and from 2 we jump from 2 to 5, right? Basically, we jump and we skip this 10 here, right? So why we're skipping 10? Because we want to get the maximum value of everything, right? So that's why we're trying to skip the as many negative numbers as possible, right? And then if it's a like an integer, if it's a positive integer, then we know, okay, fine. We we want to we, we don't want to skip them because that will make the subsequence have have a bigger uh sum, right? And when it's like a negative no, negative 10 here, right? We want to skip that. In this case, we can just skip minus 10, right? And then the final result will be this one. That basically that's going to be our biggest sum. So let's take a look at another example here, right? For example, this one, we can still case also 2, which means we can still skip at most one uh, uh, one negative one element, right? But in this case, there are like three consecutive consecutive negative numbers here, right? So as you can see, we can only skip one at a time, right? And that the next one is we cannot skip that. So from here, 10 to minus 2, right? We can either skip 2 and then we're at minus 10 and we cannot skip minus 10 anymore, right? Because that will make this the distance uh, greater than k. So we have to keep 10, but we can then skip minus 5. Or we can uh, from 10 to negative 2 we don't skip, but we skip minus 10, and right, and then minus 5 and 20. That's how we get the relative the relative like biggest sum, right, among all the possible ways. Okay, so and this is like we can solve this problem with the DP idea here. Basically, this is like I think it's a classic knapsack problem. Basically, as DPI, right? And since this is like a array here, right? So we can just use 1D DP array to store all the states. So the DPI means from 0 to the current index, what's the maximum sum, right? Then what so how can we get this one from maximum sum, right? Remember, since we're uh, it could be like we could get DPI from multiple state, right? It's different as the other one. You know, if you guys remember the other, like if you try to find the summarize the maximum sub consecutive subarrays, right? That which mean in that case it means we can only get to DI state from DI minus one, right? Because they are consecutive. But in this case, it's not, right? In this case, we can skip. We can skip at least at most k minus one element, right? So so it means that let's say there's like so here we have I, right? We have I, and then we have a I minus k minus one, right? Until I minus one, right? So this is a case window, right? And this is I. So within this case size window here, anyone can jump into I directly, right? So that's the difference here because as every time when you see like case size sliding windows, if you want to solve this one with the DP solutions, you have to use like you need to use like this basically this gonna be the maximum of DP I minus k minus 1 to DP I minus 1, right? Plus current number, right? So that's the difference with the traditional one because here the DPI the DPI will can be deduced from any of those, right? And well, actually, if you guys remember, there's like another easier like DP problems. Basically, it's the same similar description. You're also given like a race here with a either positive or negative numbers here, but there's no case here. Basically, it just asks you to find the maximum sum of a continuous subarray here. So how if you guys try to recall that's problem, what do we do about that, right? We also create a DPI here, right? D DP, sorry, a DPI here. And since for that problem, since all the subarrays they have to be I mean continuous, right? So we can only get the DPI from DPI minus one, right? I minus one, and then what do we do? We do basically we simply do a sorry, we simply do a max of the DP I minus one and zero, right? Plus current number, right? So that's how we solve that easy problem with the DP idea here because the reason we're using a max compared with zero is that if like if this DPI minus one is smaller than zero, right, then we will simply use zero because we don't want to carry over any of the negative values to the current state, right? Basically, if the previous state has a negative value, then we just simply discard it, right? Because that will make our current state has a less sum, right? Sum, right? Okay, same thing here, right? Same thing here. Basically here, max of that, and then we also need to add like a not not only we need to compare everything from dp I minus k minus 1 I and to my I minus 1, we also need to compare with the added 0 here, right? Because let's say if everything basically if all of them the maximum around among them is always it's negative, we still want to like bound set a boundaries upper bound, sorry, a lower bound for the previous like result, the maximum result is 0. Same concept here, right? If everything from the previous state is negative, then we will discard all of them. We'll just use 0. All right. So that's the first idea here, right? And okay, so with that, right, and then the problem comes down to I mean, how can we find the with this case like window, a case window here, how can we find the maximum value from this case sliding window, right? As you guys can see here, so the k can be up to 10 to the power of 5 length, which is pretty big, right? So basically, it means that if we use brute force or like we just simply search, you know, for DPI we need n, right? We need n, and to find the maximum values for DP for case window, right? We'll be also using an n with traditional way. Basically, we loop through everything in here, right? We find the maximum, and then in the end we'll get like n square, right? And with this kind of like 10 to the power of 5 quantity, this will TLE. So with 10 to the power of 5, so our algorithm has to be either n log n or n. All right. So for n log n, with this like DP for this problem, we can use a priority queue, right? Basically, since we're going to get the maximum, right? So when we're gonna maintain like a priority queue, like the and every time we see a new we move basically we move this like this I forward. Every time we see the I here, right? We will update this priority queue. Basically, we'll move this the last element out of the sliding windows, and then we'll check. We'll check if this last element is the first element in the priority queue. If it is, and then we pop the priority queue, right? Because the priority queue will give us the current maximum, a maximum value for within this range of k. And with priority queue, the time complexity to maintain a priority queue is n log n, right? Uh, sorry, it's a log n. It's a log n. Let's see, yeah, yeah. So for priority queue, the push and pop, the action is log n, and for n, and then we times n, so the total will be n log n, right? And there's also like a even better state structure to to make this time complexity from n log n to n. That's called monotonic queue. Basically, like in this case, it's gonna be a decreasing queue, right? So this decreasing queue, like, is maintained, right? it's maintained. The first element of the decreasing queue will be the current the current maximum number within this k range, right? And to maintain like a decreasing queue is is n, right? So and the each insert or update or a pop for the DQ will be for the Q will be 101, and with its n element it's still gonna be like the total gonna be n plus 2n, right? It's gonna be a 3n, which is also like an O(n) time. And okay, I'm gonna try to write the code now. The code is not long, but the idea behind it is kind of like so you guys have to I mean remember that basically every time when you see it's like when you try to get like a minimum or maximum value from a sliding window, the best way is to use the mono queue, the monotonic queue, right? And that can make this time complexity to a O(n) time. Okay, so with this DP1 here, with DP and with this two of this like boundary set as a lower boundary to 0, and with this like mono queue to keep track of the maximum values within the range k, we can start our coding. All right, cool. So uh, first I'm gonna create a decrease queue, right? It's gonna be a collections of the DQ and and a length of n of the numbers, right? And then of course the DP, right? Excuse me, the DP. So and okay, so the DP is this. So one thing to notice here that we use the n here, so not n plus one, and then so in that it's safe that we set this one to 0. Otherwise, if you use an n plus one for the first element, we have to set it to what to a negative maximum number because the, the result could be below 0, right? If we have an unused space that has a 0, that will affect our final result. Basically, if there is a like if the biggest one if the biggest one of our calculation is a negative number, but we have a some orphan 0 here in the DP array, right? And then in the end, when we do a max of DP, we'll get 0 instead of that correct negative number, right? So and now so I'm gonna enumerate, right? Enumerate nums, right? So basically, so every time, right? What do we do here? We every time when we moves into a new like positions, we're gonna update it, right? We're gonna update our decreasing queue first. So how do we update? What do we do? We try to basically once we're in the I here, right? And hmm, so well, we check if we need to pop, if we need to remove the pop the first element from this decreasing queue, right? Basically, if this one is not empty, and end of this DQ queue, the first one is the same as the element that is about to move is about to move outside of the sliding window, right? So which means that the element will be moving out of the sliding window is the nums from current I minus k minus 1, right? Then if that's the case, we simply do a pop, right? So what does this mean? Okay, let me draw a quick example here. So uh, basically, this is the element out when we are at I here, right? So this is the I minus k. Let's say here 10 uh, minus 2 minus 10. Okay, so we're at I here, right? So the I is the let's say the I is here. I is 2, right? And the k is also equals to 2. Uh, I equals to 2. So uh, since this like okay, let's have another number 4 here, right? So I think that will be better here. So and if this is 3 here, right? 0, 1, 2, 3. I equals to 3 and k equals to 2, right? And then which number will be the one that's being moved outside of the sliding window, right? It's the we are at I, right? And then so basically either 10 or minus 1 can be jumped to our current like window, right? But the 4 is the one that will be moved outside of the sliding window because sliding window is the size of 2, right? The sliding window was here before we move from minus 1 to minus 2, right? Now, since we move the sliding window to the right by 1, the sliding window will be at this. I will add the 10 minus 2 and this one, not 4, the this index, right? So this index will be moved outside of the sliding window. And then remember here, I think I made a mistake here. So remember here, the decreasing Q here, it stores the DP value, right? The DP, not the numbers, right? We stores the maximum numbers we can get at this position, right? At this DP position. So basically here, so first, to make sure the this won't the DP won't get any negative values, right? We have to do uh, if the I is greater than k, right? When I is greater than k, then we can do this, right? Otherwise, the DP will have a negative value, which doesn't make sense. And so if I is greater than k, then we can try to remove the element from this index out of the sliding window. And by doing that, we will try to update our decreasing Q. Why, right? So the way we are updating is we check if the DP element is being moved outside of the sliding window is our maximum value, right? If it is, then we know, oh, we lost our current maximum value. We have to pop this current max value out, right? And then it will give us the next one will be the current max value. If it is not the biggest value, right, then we don't do anything because we still have our current max value somewhere, right? Later on, later on somewhere. For example, this one, right? For example, this one, the current max value is at this moment is 10, right? And by removing 4, sorry, it's not the yeah, I was confused. So it's not the actual number, it's the DP values here. It's the maximum of the DP values. And if the one it got removed, let's say if the DPI minus K minus 1 is not the maximum value inside of this decreasing queue, then we don't have to pop it because we still have the within the current K range, we still have our maximum value, right? So that's how we update our decreasing queue here. And now it's time for us to finish the DP function, right? So basically the DPI equals to what? Equals to maximum, right? Maximum of the remember the first ones we stored in the decreasing queue is the maximum value of the DP, which is exactly what we need now, right? And then remember we have to set up the upper bound, the lower bound with 0, right? And then a plus number, all right? And since we are having this one, after that we also need to maintain uh, our decreasing queue, right? Basically while decrease queue is not empty, and right, and the decreasing queue dot q dot the last element, right? The last element. So it should be pop left because the first one is the biggest, so that's why we do a pop left. It's smaller, right? Smaller than the number. Sorry, smaller than the sorry, DPI. Yeah, yeah. Always keep in mind we are maintaining like DP values in the decreasing queue, not the current number. Uh, then we simply do a decreasing queue dot pop. All right. Then in the end, we do a decreasing queue dot append with the current DPI, right? And in the end, we simply return the maximum of the DP. All right. Yeah. So that should that should just do it. Let's try to run it. Hmm. Out of index. Oh, here I think. Yeah. So at the beginning, this decreasing queue, it could be empty, right? There could be nothing in this decreasing queue, and which means, right? Let's say, for example, the first I when we enter this thing for the first time, right? There's nothing in the decreasing queue, and so if we do a d dq 0, it will be out of the bound, out of the index. So we do a um, if dq else 0, right? If there's nothing, we simply do a 0, 0, 0. All right, cool. Let's try to run it. Yeah, okay, so it's passed. All right, so let's do a recap here. So a few sub problems here. First one is a DP. So the main idea here is the DP. So you have to come up with this like the DP function here. Basically for the current DPI, there are like a k ways. There are like k ways you can get to the current DP, right? That's from the I minus k minus 1 to I minus 1. And among all those k ways, we need to get the maximum between them, right? And also, and then the next one will be between the maximum. We also need to set a lower bound to 0 because we don't want to carry over any negative values, right? If they're all negative, if the maximum from the previous state is negative, we simply discard all the previous state. We just have a fresh start, right? So that's number 2. And the number 3 is the since we have this like huge, kind of pretty big inputs uh, quantity here, We cannot use like a naive linear search for the maximum values. We have to either use like a priority queue to maintain the maximum, or an even better data structure, which is what we are using here. It's called a monotonic queue. We're using a decreasing queue, and we're using a decreasing queue to maintain the current within the current case window range. What's the biggest value among all those DP values, right? And then we just the first step will be update update that the sliding window, and then with the updated sliding window, we calculate the current DP with the maximum value inside of the decreasing queue. And then in the end, we update our DP window, sorry, we update the decreasing queue again, right? Since we have this like a new number here, we'll try to pop before anything before the current I, which has like smaller number, right? That's how this like decreasing queue works, right? Because because with this current bigger value, right? With the current bigger value, which even has a bigger index, the previous smaller number will never get picked because we need the maximum value, right? Because we need the maximum value. Basically, the later one has a since the later one has a higher values, the previous smaller one, it's useless, right? Because we're trying to get the current maximum value, right? So, and this one will always get picked because our process is moving to the right, right? And this I will be moved outside of the sliding window uh, after the previous elements. And if this one has a higher values, and this will always be the ones that gets picked in here, right? That's why we can simply pop the previous like small ones outside of out of the decreasing queue. And that's how we maintain the time complexities, right? Basically every time we're maintaining this like queues here, right? The pop and append is only O1, and we're basically in uh, we're basically pushing at most n element, and also popping at most n element. So the total operation of this queue is 2n, right? And plus the the outer loop is also an n. So the total time complexity for this is 3n, which is on, right? And the space complexity is pretty. So dq is n, and the dp is also n, so it's also on, right? Uh, cool. So very cool. So there's like I think for this monocube problems, there's also like a very similar problems. It's like a little bit easier than this one, but using the same concept. I think it's number 239, and it's basically using the similar concept by maintaining like a decreasing queue, but it's instead of storing the DP problem, it's storing the actual sum. So that's why it makes that problem a little bit easier than this one. This one just combines several ideas into one problem. Okay, cool guys. I think this video is a bit long because I there's many things I want to talk about in this problem. Okay, I think hope you guys enjoyed the videos. Thank you so much for watching it, and stay tuned, and I'll be seeing you guys soon. Bye bye.